Part 1 Technology Paradox. Have you ever looked at an old bridge? Really look at it and wonder how anyone ever built it. We are taught that these majestic stone bridges were products of the 17th and 18th centuries, a time when power came primarily from human muscle, wooden pulleys, horse-drawn carts, and primitive tools. But when a structural engineer approaches these structures, the first question is not how beautiful they are, but how did they do it? Perfect stone arches require near-perfect precision in load distribution. Without modern measuring and material cutting machines, even a small deviation could cause the entire arch to collapse. So how did the builders of the time achieve results that even today's technology sometimes has difficulty replicating? Stone blocks weighing tens of tons are fitted so tightly that they cannot be inserted with a thin blade. This could only be achieved with extremely sophisticated surface processing techniques, the kind that would not have appeared in a society with only bronze hammers and steel chisels. The puzzle does not end there. Many bridges appear on ancient maps a whole year before they are officially recorded as built. What does that mean? If a bridge existed before history claims it was built, then we simply have to reconsider the whole story. It is very possible that these bridges were not built by people in the 17th-18th centuries, but inherited by later generations. They found them, used them, and then added decorative layers or reconstructed the upper part, while the core had been there much longer. When modern structural modeling methods are applied to the analysis, the paradoxes become even more obvious. The ancient stone arches are so perfectly balanced that even the slightest deviations are absent. This shows that the builders not only understood, but also mastered the mechanical principles that took modern science hundreds of years to systematize. The question is no longer, how did they do it? But who really built these things? And why did all records of them disappear? Part 2 Global Architectural Fingerprints. When examining hundreds of stone bridges across Europe, Asia, the Caucasus, and the Middle East, one unusual thing becomes apparent. Their construction techniques are almost identical. From the arch shapes, the proportions of the stone blocks, the mortarless joining techniques, to the carving patterns, all bear a common mark. This contradicts the notion that each region developed independently. For if cultures developed separately, why did they create the same type of structure? Why do stoneworking techniques in Italy coincide so strangely with those in Uzbekistan or China? Some bridges have patterns that are cymatic, that is, mimicking the geometry of sound waves. This cannot be a coincidence. Understanding cymatic geometry means understanding frequency, vibration, and resonance. While 17th century Europe had no concept of acoustic physics at the structural level, these coincidences are not signs of cultural exchange. They are signs of a shared technical standard. In the same way that modern concrete bridges around the world today follow the same standards. That is, there was once a common civilization without borders, without cultural or national divisions. an engineering that spanned the globe, with a common school of design, a method of construction, a structural philosophy. Today, we call the shadow of that civilization by a single name. Part 3. A misunderstood relic. Prague's Charles Bridge is often described as a masterpiece of medieval Gothic architecture. But when looking at the structural engineering, several anomalies immediately appear. First, the precision of the stone surfaces is beyond medieval standards. The stones were not roughly chiseled, but were ground to a level that could only be achieved with high-speed machines, similar to modern tools. Second, the records of the 19th century restoration team show that they were unable to replicate the stone-cutting technique of the original. They admit that their technology, which was more advanced than that of the medieval period, still could not produce the perfect joints of the original. Third, the deep underground foundations are completely different in style from the upper part. The stones here are larger, better processed, and appear to have existed long before the upper part was built. This has led to a growing acceptance among structural analysts. The Gothic part of the bridge may have been just a shell. The foundations and main structure are from a much older period, possibly the Tartaria, which predates the medieval period by centuries. When the earliest photographs emerged, many of the original details had been lost in restoration. Many of the patterns had been cut away. Some of the strange metalwork had been removed. No one could explain why. It seems that there was an effort to make the Charles Bridge look consistent with the official historical, but that also revealed the most important truth. The Charles Bridge is not medieval. It is of an earlier industry. Part 4. The Fourth Bridge. Scotland. A structure of two ages. Scotland's fourth bridge is often seen as a symbol of the industrial age. But when you dig into the technical data, a surprising paradox emerges. The bridge's steel is not the same age as the stone foundations below. The granite blocks at the base of the bridge have levels of surface erosion and crystallization that suggest they may have been several hundred years old before the Victorians built the steel above. Even the metal purity of the bridge is unusual. Metallurgical analysis shows the steel has a suspiciously low level of impurities, lower than the standards of 19th century mills. To create such a pure metal would have required metallurgical technology far beyond what was available at the time. Early sketches of the Fourth Bridge project even hint at an existing foundation structure, as if the construction team had worked on an existing skeleton rather than starting from scratch. The most likely conclusion is the Victorian steelwork was erected on a foundation belonging to another stage of engineering, more sophisticated and unexplained by history, a relic of Tartaria, repurposed to suit later industrial needs. Part 5. Alcantara Bridge. Spain. The Alcantara Bridge, located in the middle of the Tagus Valley, is often attributed to Rome and is dated to the 1st century AD. But when analyzed from the perspective of octopus engineering without historical architecture, structure immediately reveals a series of paradoxes. that suggests it may belong to a much older and more advanced stage of engineering. The first point of confusion is the material and treatment of the stone. The granite blocks were cut using the polygonal construction technique in which polygonal surfaces fit together like a picture. This is not the standard Roman style. Classical Romans mostly used brick, limestone, or standardized rectangular blocks, but Alcantara uses massive blocks, weighing many tons, worn into intricate patterns, something Rome was not at all famous for. The stone surfaces of the Alcantara Bridge were polished to the point of being useless. This required a deep understanding of the properties, hardness, and resistance of the material. This truncation was achieved almost by modern machine work. This was not the result of hand chiseling, but of a stoneworking art capable of creating a working model, a paradox that Roman history has never explained. Another oddity: the main arch of the Alcantara Bridge has a curvature that is almost perfectly similar to the catenary curve, the optimal geometry for distributing compressive forces. Yet the catenary model was determined mathematically in the 17th and 18th centuries, that is, some 1,600 years after it was required to build. In other words, the Alcantara Bridge applied a principle that the Romans did not know. If it is a coincidence, then the precision of fair use would exceed chance. Another paradox lies in the bridge's foundations. When examining the foundation layers, engineers found that the granite in the lower part of the bridge was more deeply weathered, that is, older than the upper part. This suggests that the bridge span had undergone multiple accretionary stages over time, and that the ancient foundations belonged to a pre-Roman civilization. Indeed, some of the blocks here resemble the polygonal construction style of Peru, Japan, and Anatolia, where polygonal cutting techniques appear sporadically as traces of a common school. A key question was how to transport 10 to 20-ton blocks of stone at speeds 45 meters above the Tagus. The Romans had pulley technology, but raising such large blocks at near vertical angles required steady traction and mechanical equipment that was not documented at the time. Even with hundreds of slaves pulling, the problem wasn't the pulling power, was the precision with which each stone was placed, with even a centimeter of deviation causing an immediate bubble. What's more surprising, there are no detailed Roman accounts of the Alcantara's construction for such a large and important bridge. The lack of records is unusual. This has led some architectural researchers to strongly suggest that the Romans simply appropriated or repainted the bridge in the same way that many later civilizations built shrines or gateways on top of ancient foundations. If we consider the Alcantara as a Tartarian or pre-Roman construction, all the pieces fit together immediately. Polygonal engineering, high geometric precision, optimal energy distribution, extraordinary durability, and the lack of a construction plan. It all came to pass. The Alcantara Bridge is more than a relic. It is the most elegant trace of an ancient school of engineering that eludes modern historical understanding. A bridge that does not belong to Rome, but to a civilization whose traces we are only now beginning to trace. Part 6. Resonance, energy, and the real purpose of bridges. When we analyze bridges from a purely structural perspective, we see technical superiority. But when we look at them from a vibrational physics perspective, the story becomes much deeper. Many old documents record strange phenomena around these bridges. Humming sounds coming from the bridge body, magnetic fluctuations, strange lights appearing at night. These things do not fit with the normal travel function. The stone arch structure is a natural resonance amplifier. If the stone blocks are arranged in the correct proportions and fit perfectly, the entire bridge can act as a powerful resonance chamber, able to interact with the magnetic field and even the energy of the environment. When combined with the water flowing under the bridge, this system could form a kind of periodic oscillation. If that were the case, then the ancient bridges were part of a larger network, a global energy system. World War II RO radio experiments further support this hypothesis. Many ancient bridges responded to radio waves in unusual ways, as if they were designed to interact with the frequency. In other words, these bridges were not originally intended for transportation. They were part of an ancient energy machine. Part 7, final part, the forgotten network. After considering everything, the advanced stonework, the global architectural fingerprints, the bridge foundations being older than the upper parts, the resonances, and the lack of construction records, the picture becomes clear. The bridges we walk on are not of recent times. They are the remnants of an ancient engineering network, a system that may have used resonance energy to serve a purpose we no longer understand. Many structures have been stripped of detail, hidden, reworked to fit the official historical narrative. But it is the traces that remain that inadvertently reveal the truth. The question is not whether Tartaria existed, but what are we standing on? A global energy network, a unified engineering that goes beyond what history records, or a civilization that someone tried to erase. These bridges do not simply connect to shores. They connect us to a chapter torn from the history books. A chapter that only when we ask the question, will the stones answer?